427 degrees centigrade, and it's dropped into 200 grams of water at 22 degrees centigrade. It gives you the specific heat of gold. Calculate the final temperature of the mixture, assuming no heat loss to the surroundings. So the first thing I want to do is I want to draw a picture. Okay? Now, you guys may think that this is silly, but trust me, no matter how simple your cartoon is, especially in physics, if you draw yourself a picture, you're going to be a lot better off. Okay? So here's what we got going on. I don't have red, even though that would be fitting, right? You have this piece of metal here, which in this particular example is gold, and it is hot. And you are going to drop this gold into this water. Now, what would the heat leave with? Is the heat going to leave the gold, or is the heat going to leave the water? It's going to leave the gold. All right, so that means whatever the equation is for gold will have to have a negative sign on it. All right. And so, will the water temperature go up or down? Up. You would be surprised at how many people take this test on Thursday, go through all of this algebra, what to do. Find out that the water temperature goes down and goes home happy. All right. So, let's take a look at the data. We have two things. We have an equation that describes the metal, right? And we have another equation that describes the what? The water. And it said, assume no heat loss to the surroundings. You see, this is how thermodynamics gets to be kind of complicated. There's lots of ways why it does. But, you see, if heat lost out of this beaker, you got to account for that. Well, how much heat do you think would be lost out of this beaker? Well, see, no one knows. And anytime something changes and you don't know how much, that's a differential equation. All right? So whenever you put this hot metal in here, if it fizzes or if it evaporates, well, how much does that evaporate? Again, you don't know. So that's another differential equation. Before you know it, you have systems of differential equations, and that is an ordeal to get that figured out. All right? But this problem says assume none of that happens. Don't even think about those issues. Here's what we've got. We've got gold. So the mass of the gold is going to be 325 grams. Now the specific heat of gold is going to be 0.131 joules per gram degrees centigrade. Now where did I get these numbers from? The problem. All right? I just don't give birth to these numbers. They're there. Now, we're going to have the final temperature of the gold. We're going to have the initial temperature of the gold. Okay, how hot was that gold initially? Does it tell you here? How much is it? 427 degrees centigrade. That is the initial temperature of the gold. All right. Now, that's all we know about gold. But we got another problem. We got water. Okay. So we're going to do the mass of the water, specific heat of the water, final temperature of the water, initial temperature of the water. Okay, what's the mass of the water? Well, it says right here that the mass of the water is 200 grams, right? So see, someone's taken a balance and they've weighed that. That's going to be 200 grams. Now, how many milliliters is 200 grams approximately? 200, right? Because the density of water is 1 gram per milliliter. So for water's case, the mass in grams and the volume in milliliters are very similar. All right. Again, I told you could sharpshoot me on that because the density of water is not perfectly 1, but it's close. All right. Now, what's the specific heat of water? 4.184 joules per gram degrees centigrade, right? On the back of the test, you're sitting there and you're reading that, specific heat of water. And the initial temperature of water is in this problem here. 22. All right, you guys are on top of this. 22 degrees centigrade. Wow. Okay. Well, that's all we know. So everybody's in agreement that when you take hot gold and put into cold water, the gold will get cooler than it was, and the water will get warmer than it was. Okay, so we've got two equations. The heat of the gold equals the mass of the gold times the specific heat of the gold times the final temperature of the gold minus the initial temperature of the gold. And the heat of the water equals the mass of the water times the specific heat of the water times the final temperature of the water minus the initial temperature of the water. So now we got two equations going on. All right. Well, praying to the chemistry people that there's not four. All right, but there's two. Okay. So now you guys told me that the heat is going to leave the metal, right? So let's take a look at this. Now I want you to write that down, and I'm going to say something like 3 times on purpose. And if you just watch my fingers, okay? The heat that leaves the gold goes to the water. All right? In other words, the heat that leaves the gold is directly transferred, that's what the equal signs mean, to, in the form of heat, to water. So that's the mathematical way to say that English sentence. Assume no heat is lost to the surroundings. And this is why people think word problems are so hard, is because you've got to take assume no heat is lost to the surroundings and get that. Now who would have been able to do that without a lecture? All right? So that's the thing with chemistry, is you've got to be able to distill this down. The heat that leaves the gold is transferred in the form of heat to the water. All right, let's do it. Aha, how does that look now? All right. So now at least we've got one master equation. And you can always tell whenever you're teaching an introductory course, people are looking at that and going, oh my God, right? And as you get older and you get in your senior classes, people look at equations like this and we're like, thank God we finally just got one equation, all right? Not 15. Okay, so we all know what a negative sign is. We're just bringing it down. Now, what's the mass of the gold? Well, let's go over to our nifty-difty table. It is what? 325. So we'll check that off as we've done used that. Now, I'm going to suppress the units here for clarity. Now, I am pretty confident that my final answer is going to be in degrees centigrade. So I'm suppressing the units to kind of help you out a bit. The specific heat of gold is 0.131. The final temperature of gold, we don't know. X, right? We don't know. Is there a number here? Not a number there. We don't know what's going on. All right. The initial temperature of gold, though, is 427. All right, we know what's going on there. See, we've used every piece of information we can from gold. Now let's go to water. All right, the mass of water is 200 grams. The specific heat of water is 4.184. Now the final temperature of water, let's call that Y. Do you see a number sitting here? No. Okay. And what's the initial temperature of water? 22 degrees. Okay. On the surface, it looks like we have ourselves a problem. We've got one equation with two unknowns. All right. That ain't going to work. I don't care how much math you've had. If you have one equation with two unknowns, that ain't going to work. Some people say there's no solution to this. No, there's an infinite amount of solutions to this. No matter what number you choose for X, you can massage it to get a number for Y. So there's an infinite number of solutions to this. So we either have to find